Grüezi YouTubers, here is the guy with the Swiss accent again.
A self-balancing robot is a fascinating device. Because of the cheap sensors, we can build such a device at home and have lots of fun with it. In the next few episodes, I will show you how to build a self-balancing robot based on an Arduino, how to build a remote control based on an nRF24L01 chip, and how to enhance the robot with autonomous driving using 3 ultrasonic sensors and an A-Tiny. To build a self-balancing robot is still not a simple task. Just the sketch uses more than 90% of the resources of an Arduino Pro Mini. Any self-balancing device needs at least 3 components: motors, an accelerometer, and a microcontroller. The accelerometer can measure the angle of the robot, and the microcontroller uses a PID controller to make sure that the angle is always 0, which means a vertical position. If you do not know how a PID controller works, I enclose a link to one of my former videos. Such a robot usually does not stand completely still. It always has to move a little around the ideal position. As soon as I push the robot, the sensor detects a big difference between the vertical position and the microcontroller and sends signals to the motors that they correct the position. Of course, this can only be done in certain limits. This is why self-balancing robots fall down if they hit an obstacle, for example. Now let me show how I built the robot. This robot is based on the work of Jose Julio and his Bee robot. I enclose links to his video and homepage. However, I changed the software more or less completely because I wanted to understand how it works. I started with some 3D printed parts. In addition, I used 2 NEMA 17 stepper motors and the respective drivers. I could have used a normal Arduino Pro Mini or similar microcontroller and an independent accelerometer module. Because this combination is also used in quadcopters, I decided to use a MultiWii 2.5 board, which has all needed components and connectors readily available. The power source is a 7.4 volts battery. Because the MultiWii has no voltage regulator, I need also a 78L05 to reduce the 7.4 volts to the 5 volt for the electronics. The motors run at 7.4 volts. After printing all the parts, I built the frame with the integrated stepper motors and mounted all electronic components. Then I built a cable harness to connect the various modules. I use my technique of DuPont wires, which I presented in another video. You also find the link below. The only place I cannot use ready-made DuPont wires is for the connections of the motors. Here I have to crimp the 4-wheel connectors the conventional way. And you see, this is very slow compared to the usage of ready-made wires. The advantage of such a cable harness is the assembly speed. With proper planning, you are also quite sure that all connections work and you do not destroy any components. Here another trick. Use the colors of the wires wherever possible. For example, I never use black for VCC or red for ground. This is way too dangerous for me. After I assembled the whole robot and checked the wiring again, I can now load the sketch and test the system. Fortunately, I have no problems and it runs. This is of course only possible because I built another robot some times ago, and I had a readily available software. You find a link to GitHub with the sketches and the wiring plan. Let's now turn towards the software. It consists of the initialization routines and the interfaces for all sensors. The main loop, as usual, is programmed as a state machine with 4 states. The states are obviously up and down and 2 states in between. The status getting up is currently not used. Here you could change the PID controller factors for a more aggressive behavior. The main work is done in the 2 subroutines get angle and movement. Get angle gets the angle from the accelerometer, and movement consists of 2 independent PID controllers. One to keep the upright position and the other to control the speed. This part of the code is still based on the work of Jose. First, the get angle subroutine. The routine is straightforward and I did not use things like Kalman filters to process the signals of the accelerometer, because it was not necessary for this purpose. The robot works anyway. The reading of the MPU 6050 chip is based on a library of Jeff Roberg. Now we go on to the movement subroutine. For today, only the controller for upright position is in the focus. This is done by the subroutine stability PD control. For this controller, we only use P and D factors. These factors are absolutely critical for the behavior of your robot and are very difficult to find. When I started with my new robot, I had no clue how big these factors should be. This is why I had to develop a remote control with bidirectional communication. With this system, it is possible to change these parameters on the fly and see the reaction of the robot. It is also possible to display other values which were important in this situation. Be prepared that you have to go through a similar exercise with your own robot if you change something like the motors or the geometry of the robot. Now some words about debugging of real-time systems like a robot. The entire loop of the robot takes less than 10 milliseconds, which means that the values change more than 100 times per second. Serial print is way too slow for that, because you cannot read the changing values fast enough. The transfer of the values via air to the remote controller is also too slow. The only real possibility to debug such fast processes is the use of digital to analog converters and an oscilloscope. Maybe I will do once a video about this topic. In the next video about the robot, I will focus on the two-way communication with 2 NRF24L01 chips. These modules are very cheap and you get also long-range versions of them. And the transmission speed is fast enough to remotely control your robot. The part of the sketch called remote control belongs to this topic and will be discussed then. If you read through the code, you will discover a whole section about autonomous driving. This section will be discussed in a later video where I show you how I built a distance sensor with 3 ultrasonic sensors and an A-Tiny. This is all for now. I hope this video was useful or at least interesting for you. Bye!